Today we're going to tackle one more problem about radioactive decay, integrated rate law, and half-life. We're given this question where uranium decays into lead, and we're given the half-life. We're also given the amount of uranium and lead found at an unknown time that we're looking for, and we're asked how old is this rock. So knowing that anything to do with concentration at a specific time, we're going to use the integrated rate law for first order. Since this is a radioactive decay, we know that in order to use this equation, we have to find value of K. So we can find the value of K if we put in our given half-life into the half-life equation here. And remember that here our half-life is 4.5 billion years. We have to convert that into years so that you don't get any weird stuff happening later on. So this is our units, always write out the units. So then the next step is using this integrated rate law. Now we want to find the concentration, or rather just the mass at a specific time, and also the initial mass. So anytime where you have a reaction going on, you know that it's going to look something like this. So anytime that there's an equation, you're going to consider this factor. The amount that has reacted, or rather the amount of product you want, is always stoichiometrically proportional to the amount that has reacted. So in our question here, we're told that there's a certain amount of uranium left. So that is the remaining amount of uranium. And then we're told that there's a certain amount of lead. So that tells us how much, that kind of hints us how much uranium has reacted. But this is not the amount of uranium that reacted, but stoichiometrically equivalent. This is not the mass of uranium that reacted because this is a mass of lead. So what we want to do now is to convert this mass into a mass of uranium so that we can find the initial amount of uranium that has existed. So to do this, we will use a simple ratio. This is the amount of uranium that, the amount of lead that we have. And we know that for every 238 grams of uranium yields 206 grams of lead. With this ratio, we're told that the mass of uranium that has reacted is around this much. By the way, you don't have to use this ratio, but it's definitely the fastest way. So if we add that to our remaining, we get the initial amounts, which tells us initially there was around this much uranium in the bargain. So that means with the initial amount, we finally have something to put in here. And we're finding the T. We already know the value of K. 1.5 times 10 to the negative 10. And then what do we put for our mass at a certain time? So the time is the age of the rock, but it's also the amount of time that has passed to facilitate this reaction. So the mass that is remaining at this amount of time is just the mass that remains, which we're given here. And now we want to do the algebra. So if you ln this side minus ln this side is the equivalent of saying so I can remove this side. And then we can divide all of this. And this is in units of years. In essence, the number that we're gonna get is going to be around 1.7 times 10 to the 9 years. So that's 1.7 billion years. So to recap, after 1.7 times 10 to the negative years, 10 to the 9 years, that is the amount of time in order to have this much uranium left. So big takeaways in terms of steps is definitely remember to do this part, don't overlook it. And also remember to use this ratio to find the stoichiometric equivalence of your products back to your reactants or the other way around. And definitely remember units, otherwise they might trick you up, like billion. And there you have it.